Yeah, cool. So I'm with Anyscale. My name is Rehaan, and I help lead the fine-tuning efforts at Anyscale. And I'll kind of discuss in this presentation some of the insights and cool things we've learned about LLM fine-tuning, and hopefully you can find some of those insights useful. So before we get started, I'll give a bit of background about where Anyscale is coming from here. So Anyscale invests a lot in open source software. Ray is our flagship distributed computing platform, and it lends itself particularly well to AI and LLM workloads. So a lot of key industry players trust Ray for their AI and LLM workloads. OpenAI trained ChatGPT on top of Ray. Uber, Cohere, recently ByteDance, the company of TikTok, uses Ray to manage multimodal LLMs over hundreds of terabytes of data. So AI and LLM workloads are pretty central to who we are as a company. And as a result, an area that we're interested in is LLM fine-tuning. So I'll discuss some results from a recent blog post we had. We released about a month ago, and it got some good traction. And in the blog post, we kind of build a comprehensive argument for why fine-tuning on top of open source models makes sense, even when compared to models like GPT-4. So there's some cases where it makes sense, there's some cases where it doesn't, and we kind of do a comprehensive case study of this. And so I guess the TLDR of this blog post is the following chart. I don't know how well you can see it, but over 3 tasks, we show that these 2 tasks, functional representation and SQL, starting with the Llama 7B model, if you actually fine-tune and do end-to-end evaluation, you actually get better numbers with the both Llama 7 and 13B models when compared to GPT-4. And so this was a pretty cool result where we realized, obviously not only are the Llama models cheaper to actually deploy, but accuracy-wise, after fine-tuning, they're actually doing better than GPT-4. And the initial, it's hard to see here, but the initial numbers when using the Llama 7 and 13B models, it's pretty poor. And so fine-tuning is really able to make a substantial difference here. In both SQL generation, and then I'll talk about the second task here, which is functional representation. It's a little bit of a contrived task here, but the point I want to make is if you put the accuracy numbers aside for a second, the prompt length we needed to put into GPT-4 to get these numbers was huge. So in terms of the amount you need to pay, for both GPT-4, the number of tokens you have to input, there's some cases where fine-tuning really makes a lot of sense. And so we found the type of tasks are if you want to control the output of your model and have it match either a SQL output or some very constrained output, fine-tuning can be a really good tool for that. One of my favorite findings that we have in this blog post is actually that the data set can be a really, understanding your data set can be really powerful to unlocking the full potential of fine-tuning. So there's this data set called GSM-8K. It's grade school math, 8,000 data points. And out of the box, actually, fine-tuning doesn't do too well. So it goes from 28, with the Llama 13B model, you go from 28% to 37%. So you're given a word problem, the model has to output an explanation, and then numerical, an actual answer. And you're evaluated on the correctness of this answer. But it's only, 8,000 data points, 7,000 points of training. And so we realized if you take the initial Llama 13B checkpoint, and it's just almost in the realm of a cool hackathon project, you take this Llama 13B checkpoint, and instead train it on 30,000 data points of a data set called MathQA. MathQA is a significantly noisier data set. It's multiple choice as opposed to giving a numerical answer. Completely different structure. But if you train it on these 30,000 data points, take your best checkpoint and then train it on GSM, you actually get up to 50%. So fine-tuning can be really powerful with the right data set. Another point I want to discuss here is LoRa versus full parameter tuning. So a lot of these previous results were done with full parameter tuning, but obviously to make fine-tuning more accessible, having some more efficient way to do fine-tuning is really important. And so there's a technique called LoRa, which is low rank approximation, and basically significantly minimizes the number of parameters you need to optimize and feed gradients through in training. And we found that when using LoRa, and this has been externally validated too, LoRa can be a really powerful technique, even when compared to full parameter fine-tuning. So in these charts here, kind of hard to see, but LoRa really gets up to the same level as full parameter fine-tuning. And the final point here I wanted to make was, if you put fine-tuning aside for a second and just look at how fast open source models have been, proliferating just in the last few months, it's really interesting to see. So before July 18th, which seems prehistoric, the best open source models were these Falcon models. And if you look at how they do non-fine-tuned on this math data set, they're kind of blown out of the water by these Llama models. Even the 7 billion parameter model, outperforms the Falcon 40B model. And this is just over the last few months. And so the point I want to make here is we can probably continue to see this type of trend, with open source LLMs. There's no reason to think it would stop here. And this is good for communities like us where you're either fine-tuning or deploying LLMs for the purpose of like hackathons, this is like a really good trend to see. And with that being said, I wanted to discuss one of Anyscale's latest offerings here, which is called Endpoints. And it's a open AI-like API where with Code Llama, Llama 7B, 13B, and 70B, you can query the model and get an output. So for example, if I give the Code Llama the following input, explain the bug in the following code, it gives you, an explanation and identifies the bug for you here. And the key is, the key here, thing that we're kind of proud about is, and this was mentioned earlier, is we're looking at having the service for $1 per million tokens. So in order to get to this type of number, you kind of need to have optimizations across the whole stack, right? So from single GPU optimizations all the way to auto scaling, multi-region, multi-cloud, we have optimizations across this whole stack to be able to offer this service at $1 per million token, even for the Llama 70B model. So yeah, this hackathon will give out an API key in the Slack where we offer this for free. And yeah, you're more than welcome to use that. And yeah, final point what we have here is this Monday and Tuesday we have Ray Summit. And so if anybody's interested in joining that, you can let me know and we can offer like discounted or free tickets to that.
Could you tell us more about Ray Summit?
Yeah, so I guess Ray Summit is why Robert is not speaking here right now. He's preparing for that. But I think one cool thing about Ray Summit, we'll actually be offering Endpoints V2. We'll be announcing that product for the first time. And so with Endpoints V2, we have an OpenAI-like fine-tuning service for Llama 7 and 13B models. So you can just upload your data. We take care of everything else. It's an API-type service. We fine-tune your data, and then you can serve the model through our API as well. And so we'll release that around Ray Summit. Yeah, it's a bunch of keynotes. We have like the creator of ChatGPT, John Schulman is there, Percy Liang, Jan, a bunch of big names will be speaking. Yeah.
Someone like an enterprise approaches you with a shit ton of data, at what point do you advise them to actually do training versus just like indexing of the data? Like,
yeah, I guess like it's a dependent, it's like a task dependent thing. It's hard to answer with more information. Yeah, I guess it's hard to say.
What is one example where you definitely do advise to fine-tune?
So I guess like
it's not an easy question.
It's hard to answer without specifics, right? Typically, if someone's coming to us, they already have an idea that okay, they want to fine-tune something, and they're just wondering like how do they go about doing that, right? I guess if they haven't made up their mind, at least in the meetings I've sat in, it doesn't get to that point.
Can you pre-train a novel model architecture in Ray?
Oh yeah, so like ChatGPT was trained with Ray. So.
Oh right.
Yeah.
Damn.
So
Nice flex.
Nice flex, yeah.
Yeah.
What's some of the techniques that you've seen in converting unstructured data to fine-tunable data?
That's a great question, and I guess that was one of the challenges we had, even with the results in this blog post. I guess like if you take the example of like the GSM dataset, right? This grade school math dataset. Let's take the idea of like we want to evaluate, let's say, the base model, right? And it's outputting basically a bunch of unstructured data, and you want to find a way to evaluate that. It turns out like GPT-4 is like a really common, great way to kind of turn unstructured data into fine-tunable data, and you get like pretty good numbers there. So if with the Llama models, for example, in their base format, you give it a math problem, and it spits out an answer. The non-fine-tuned version typically never adheres to this format over here. So you need to send it through GPT-4 to actually like get the numerical answer. Or like with the SQL dataset, we needed to do some like some filtering and denoising and restructuring of data with GPT-4. So it's like it's a fairly common technique. It's not to be ashamed of, I guess, if you're trying to fine-tune.
Say for restructuring the data,
Mm-hmm.
is it truly done by prompt engineering or?
So I guess it's at least in our data sets here, I guess like with GPT-4 there was some amount of prompt engineering to get like the right output of data. We played around with that a little bit. Yeah.
Could you tell us more about how OpenAI is using Ray? Like, is this just for like the ChatGPT training?
Yeah, this was
using it for serving.
for orchestrating the training for ChatGPT, as far as I know, like the training side, and I think with Cohere as well, training LLMs for Ray.
Not for inference.
I'm not sure. I know for ByteDance, which was behind TikTok, they use it for like multimodal inference in serving. So, yeah.
When fine-tuning Llama 2, did you notice any like performance difference between the chat models and the base models?
That's a great question, yeah. So we kind of just out of the box started doing the base models. I think initially we had done some preliminary tuning on top of chat models, and basically it depends on your task, right? So with the math data set, the chat tune models out of box do a lot better than the base model, likely because they might have been trained on GSM and like chat tune. And so for that reason, like it makes sense to start with the base model, given that the chat tune model might already be in some local minima, where you know, for a task like this functional representations task, I haven't run it, but I could absolutely bet money that the chat tune model would do worse if I had to fine tune on top of it, because it already has been, you know, trained with data that's not this.
Yeah.
And so you want to start with a more vanilla model.
I have a follow-up question.
Yeah.
So a lot of people fine-tune with like the alpaca like instruct dataset format where it's like, you know, instruction, input, response, right?
Yeah.
But with the base models, have you found that like you don't have to follow any of that? You can just do route because that's what I've been doing.
Yeah.
Like it works.
Yeah, absolutely. So that's a great question. You absolutely, when doing especially full parameter fine tuning on the base model, you throw away all the prompting and use these things called special tokens, which in doing the training process, the tokenizer learns to recognize these special tokens. And so you don't need any prompt at all. Just do the special tokens.
Yeah.
There's no system user prompt.
Cool. Yeah.
Cool? All right, yeah, that's it.
Thank you so much.